Hi, in this lesson today we're going to look at logic statements. In math, logic can be defined as the use of symbolic and mathematical techniques to determine the forms of valid deductive arguments. When you think of logic, you think about what makes sense. It's the same as true in mathematics. The idea that evidence must be presented in the correct and sequential order in order to come to a valid conclusion. We're going to be doing this in the proofs unit in both an informal and formal way. Conditional statement is symbolized by letters P and Q, written as if-then statements in which P is the hypothesis and Q is the conclusion. So the idea is that we're starting with something, and that's our P statement, and then it leads to something else, its conclusion. It has to make a logical connection. Draw an arrow from the hypothesis to the conclusion if there is a conditional relationship. So if you could say, if the dog will chase it, then I do my homework, well then that would be an example of a good statement. But if you can't say it, then it's not. So take a pause here and write those down, then come on back. So you might have had something like this. And here we see that arrows in this case can work in both directions, and some of them could be interchangeable in terms of the if-then statements. But in all situations, we're starting with something, and it is leading to that conclusion. And the valid relationship you can see is there. Copy down these definitions into your notes. Conditional statements and symbols. Conditional, the initial hypothesis P and Q conclusion, right? So when we write it out symbolically, we use the letters P and then an arrow pointing to Q to show it's P then Q. The converse, which switches the hypothesis and the conclusion. So we'd have Q then P. Inverse, which negates, and if you see this symbol right here, this is called a tilde, and it kind of represents the word not. So negates both the hypothesis and the conclusion. The contrapositive is the converse and inverse of the original conditional statement. And the biconditional adds an if and only if, IFF, between the hypothesis and conclusion of the conditional statement. Only if the conditional and the converse are true. So that's the only way you can have a biconditional. So here my conditional statement must be true, my converse must be true, then I could have a valid biconditional. We'll look at that in an example here. Conditional statement. If it is raining, then it is cloudy outside. So we see it is raining is my P, and then it is cloudy outside is my Q. So that's my if-then statement. So I want you to take a moment to pause here and try to write each of the other statements here, the converse, inverse, contrapositive, and biconditional, whether there is a valid one or not. Okay. For converse here, you might have seen that we just switched the order. So if it is cloudy outside, then it is raining. And this is kind of indicated here, Q then P. So it started with the conclusion, then the hypothesis. Inverse. Remember what we said on the last slide about this tilde? Kind of represents the word not. Yeah. If it is not raining, then it is not cloudy. So just looking down from the beginning, right? Our first statement was true. If it is raining, then it's cloudy, because it's not going to rain unless there's clouds outside. But the converse was false because it could be cloudy without rain. So our inverse here is false. We move on to our contrapositive, in which we apply the not statements and switch the order. If it is not cloudy outside, then it is not raining, and that is a true statement. So what you want to do is looking at these statements is you want to read through them to see if they make logical sense before you identify if it's true or false. Lastly, we said the biconditional works only if the conditional was true and the converse was true. And it wasn't, but let's just write one anyway for practice here. It is raining if and only if it is cloudy outside. All right, we'll see you in the next lesson.